So, does everybody have a copy of this handout?
Yeah.
Okay. So, what I want you to do, sort of as a background, is you don't. So, so take a moment to read the first page of this handout, because it talks a little bit more about each of these cross-cutting concepts. So take a moment to read this. Just page 1. Okay, so you had to read. So the main points here is that one is that these ideas aren't new. You know, you've probably seen this before, and they've been around for 20 years. The problem is that we haven't used them well in our classroom. That's what we're trying to improve. The purpose of using these cross-cutting concepts, which you can use across the sciences, so these cross-cutting concepts have validity in life science, in physical science, in earth and space science, and they provide a lens for students to think deeper about the science concept. We're going to experience that today. But what we have to do for students is make them explicit, to really talk about these cross-cutting concepts in a very explicit way. So before we come back to this reading, I want to do an example with you. And I want to focus on one cross-cutting concept, which is systems and system models. And this morning, you heard one of the speakers mentions the importance of systems and systems thinking. So it has applicability outside science as well. So what is a system? And why are they important? Now, in science, for us to observe something has to interact, right? Because otherwise we can't see it. So, and to interact, we need at least two objects. And when we have two objects, we have a system. So that means that everything in the universe are systems, you know, from small to big. And this helps us make sense of the universe. Because the universe is very, very large. And we have to be able to cut it in pieces. And to give you an idea of the systems we're talking about, so on the largest scales in the universe, our systems are the galaxies, the solar system, or the entire universe. If you go to a smaller scale, we have systems on Earth, like ecosystems. And we're going to talk about ecosystems later on. Then, at the size of this room, we have what we call macroscopic systems, like the bottle with water is a system. And we're going to look at another system related to that sooner. Then at a smaller scale, we have atomic molecular systems, right? And we can even go smaller to subatomic systems, like we have a nucleus with electrons, or the smallest level we have nuclear systems. So we have systems at different levels, and students need to think about these systems explicitly. And we're going to do an example with you. But before we do this, there's three things that students need to think about when we think about systems. So one is, what is the boundary of the system? And what I mean with that is, when we study something in a classroom, what do we need to think about and what should we exclude? And a good example, for example, is we think about the solar system. So if we think about the solar system, what used to be the boundary was the sun, would include the sun and the planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn. The other planets were not known. Later, when we discovered more, the boundary increased. Okay? And within those boundaries, we have, I'll use this one. Within those boundaries, we have planets, and we have moons, and we have asteroids. And then finally, so we need to know the boundary, we need to know the components in the system, and then very important, how do these parts interact, right? So what are the interactions and what are the flows? So, for example,
how do the objects in the solar system interact? Does anybody know? How do they interact? Through forces, right? Through forces. So through gravity. So gravity causes the interaction and it makes them move. And the motion is mostly circular, so those are the flows. So for every system, we need to think about this. So we're going to do an example, and it's a very simple one. But once we look through the lens of systems, we can go much deeper into this. So we're going to look at an ice cube in a cup of water. And I'm going to give you a cup of water with the ice cube at your table so you can actually look at it. So what I want you to think about with the people at your table, and if you can join, maybe you can join the gentleman over there, we can work together. What are the boundaries of the system? In other words, what needs to be included? You know, so the boundary could be, is it the entire country of Jordan that we need to consider when we talk about a cup with ice? Or is it the whole center, or maybe this room? Or how big is it? What are the parts? And what are the interactions? And what are the flows, especially of energy coming in or out of the system? So I want you to think about this and talk with each other while I give you the ice cubes. So, okay, I'm gonna give you more time, but I want to interrupt you because as you are thinking about this, you probably feel a need to write or draw. And this is why scientists use models. So what scientists do when they think about systems, they make drawings or they build things to represent the system, right? So what I want you to do, based on your conversation, is to draw a model that represents this system and that represent the components and the interactions and the flows of matter and the flows of energy within that system. And you can use text and symbols. So I'm going to give you a piece of paper, and you should have a marker at your table so you can draw it. Okay? time to do this. You know, it's a very simple system. But I want you to take a moment to get out drawings that people made. And you can see the variation across the room. So take a moment, just get up from your seat, walk around, and look at the other representations.
بالبداية كان كتير سيء لما زبط. تمام. شو بعرف هلا بشوفها.
So one thing. So return to your tables, please.
مش انتوا كنتوا وحدي. أنا واحد عن بالي. أنا مرتب من مهندس خيال. قلت له مش أنا قلت لك هناخد من مهندس خيال. وإحنا بناخد العدة.
Okay. So I'm waiting for everybody to find their seat. So we want to talk a little bit more about this, right? So you walked around the room and you noticed that there's different ways to represent the system, right? Now, let me ask you, we're going to use the microphone when you respond. So what's the boundary? What is the boundary of the system? How big is the boundary? Does anybody have a suggestion? That's in. So you're saying that
the boundary is the glass cup. Just this.
Okay, so you're saying the boundary is the glass cup. Does anybody have a different idea?
I think the boundary is the air around the cup and the table, the surface that it's put on.
So you're saying the boundary is bigger than the cup. The boundary includes the room. Anybody has a bigger boundary?
The boundary is the universe.
The entire universe?
Yes.
Okay, so
according to heat transfer, energy is conserved, so it transfers from one place to the other. Heat is always there in the universe.
Okay. So what do you have to say about that?
I have a point. The boundary considers the scale of energy transfer or mass transfer. If you want to take a big scale, then you take a larger boundary. If you just care about small scales, then it's a small boundary.
So it depends
on the scale, yeah.
So it depends on what we care about, right? So we want to make it as simple as possible, because the safest thing to do is to include the entire universe. But that means it gets very complicated, because we have to include everything in the universe as part of, right? So how can we make it as simple as possible, right? So the glass cup and the air around the room, right? I think we need the air around the room. Now, so we need this room. So what are the components that we need to include? What are the components of this system? So tell me about the components. What are the components?
The components are the three states of matter: solid ice and liquid water and gases dissolved or gases above the ice cube.
Okay, so we have, so you say the components are the ice, the water, okay, the gases, the cup, okay, impurities in the water, if they exist, they could be important if you look at details. Anything else?
Yeah. Do we include the table as when I say components, do I include all the parts? Does that mean the parts of a system?
The question is, do you include all the parts? Should we include the table? If you think the table is important, then you do include it. So why may the table be important?
Heat transfer.
Okay, so the point is made that the table, may have to include the table, because the table has a temperature and there's a heat transfer coming. It's a source of energy, right? It has a certain temperature. Any other parts that are important? So are we part of the system too? why are we part of the system, and where do you see something on your cups that suggests that we may have to include us too? Okay, if you're holding the cup, okay. So, does anybody have condensation on the cup on the outside? Yeah? Right. It's very dry here, right? But if you do this when it's more humid, what do you get on the outside? The condensation, okay. So if there's condensation on the cup, where does that come from? Okay, from the air and from? And also from us, right? We breathe out water. So if condensation occurs, we also have to think about us. Okay. So we have talked about the components. So what about energy flow? So where is the energy flow in the system?
Start from ice to liquid state, then to the gas state.
Where's the energy coming from?
From the air, from the surrounding.
From the surrounding.
Around
and it
this-
goes, where does it go?
To the interior of the glass cup.
Okay.
To the all component, to the gas phase and solid phase and the
Okay, so there is temperature from the surrounding air, and that goes where? From the hotter to the colder. So is there an exchange between the air and the water? Why? There's a temperature difference. And why is there a temperature difference?
Because let's say the surrounding water has lower temperature than the air, and the ice, of course, has the, let's say,
Yeah.
freezing point.
Right, right. And what's the temperature of the water? Yeah. And why is it 0? It's in the melting stage. So the water and the ice are at the same temperature, basically, right? Because it's a phase transition. So we have transfer of energy from the air into the water, but also directly into the ice cube, right? And also into the cup, right? So what about flows of matter? What about flows of matter? Is matter moving from one place to another place?
There should be some evaporation and convection, of course.
So we have evaporation,
Yes.
right? So what is evaporating? The ice and the water, right? But also the ice, at a very slow way, is evaporating directly. There's evaporation from the water. Anything else? There may be condensation of matter on the cup. What about matter that's in the ice cube? Is all the matter staying in the ice cube, or is it also it's moving into the water, right? So it's a very simple system, but once you start thinking about the components and the interactions, you see there's a lot of things going on. And these are the things we want to talk with students about. We want them to think about this, to go much deeper into something that looks very simple, right? Okay, so my other question is, talk with your partner. So we focused on systems and system models, but which other cross-cutting concepts did you use when you were thinking about the systems? Which other cross-cutting concepts did you use? So talk with your partner. And then look at your handout. There's a list of cross-cutting concepts if you don't remember. Okay, so I have the cross-cutting concepts up here again. It's a different way to organize them. But I want to start with patterns. So patterns are really important in science because the reason we can do science is because we have patterns. And the best way to show you is, if I let this go, what happens? It moves down. Okay, and if I do it again, what happens?
The same.
Same. So when you see young children, they experiment with patterns. They take the spoon and they drop it. And then they say, well, if I do it again, will it drop again? Now we're lucky because we live in a universe where there are patterns. If we lived in a universe where there were no patterns, then if I let it go, it would go this way. And the next time it would go there. And the next time it would go there. Everything would be random. And if that was the case, we couldn't do science. So the reason we can do science is because there's patterns. And if you look at your cup, there are patterns in terms of what happens when the ice cube melts. For example, it tends to get more round as it's melting, and it happens for all of you. And the ice cubes get smaller and smaller. So there's a pattern to how things are changing. There's also patterns in terms of water condensing and where the water condenses on the outside. So patterns are really important. Now, because there are patterns, there must be something happening. There's a mechanism, and that gets to cause and effect. So cause and effect is an explanation of the pattern. So why do we see these patterns? What's the cause of them? And then we get into structure and function. Now, structure and function is a very special case of cause and effect. And it's important here too, because if I change the size of the ice cubes or the shape of the ice cubes, the way they melt is different. So you can try it out. If you have square ice cubes or circular ice cubes, and you may have seen them, sometimes they're cylindrical. And if you change the shape, the way they melt is different. Right? And then we have systems. So we got systems, and every system has a scale. And somebody was talking to me, you were talking to me, you said, can you share with the group what you were saying about scale and systems?
I was saying that one of the essential questions we discuss in our classes is, in a certain system, what will happen if you zoom in or zoom out in that system? If you look at the microscopic versus microscopic level. Right. So the interactions change, the flow change, what changes?
So when you made your drawings and when you looked around the room, you noticed that some people had drawn the system at a different scale. You know, you notice the particles in the ice were drawn into, right? And you can look at smaller and smaller scales and talk about what's happening at those scales. So that's important. Now, energy and matter. Did you use energy and matter, right? So you talked about energy and energy flow and matter flow. And what about change and stability? So what is changing in the system? Right? Yeah, the state of the ice. So the ice is going into water. So, and there may be an amount of condensation. What is stable in the system? The total amount of energy is conserved, right? But also the temperature of the water is stable, right? As long as there is ice in the water, it's pretty stable. Yeah. Yeah. Yes?
It's very cold and the surrounding is hotter, so the system is gaining energy.
From the room.
From the room. So basically, yeah, but if I take as a system the cup and its contents as a system, it's gaining energy. It's not constant energy.
So this you make a very good point, and this is why we have to be very careful to define the boundaries of the system, because conservation of energy is only true in a closed system. So the question is your boundary big enough? And that's why we talked about that. We want to include the room in the entire system, because within the room the energy is conserved. There's energy coming out of the room going into the cup. Huh? Yeah, if it is isolated, right. So tomorrow I do a session on energy and matter, and we're going to talk more about that. So what I want to do now is do one other example of systems. So I have to skip a piece because basically the whole session was cut by half an hour. But so here's another example of systems. And now we're going to, this is an example for biology. So suppose you look at a lake, right? And you notice there's a large number of dead fish in the lake. So you can see the dead fish. So what I would like you to do, as with your table, is develop a model of the system to illustrate what may have caused these fish to be dead. All right, so you want to think about, so there's dead fish in the lake, what is the system we need to consider? And then use the model to come up with questions that can help you find additional information about why these fish may be dead in the lake. And to help you with this, the same task, but you need to think about what's the boundary of the system we need to consider. So you need to think about, you have a lake, is that the boundary, or do we need to go beyond the lake? Is that important to consider? What are the components? What are the interactions between these components? What are some possible causes that these fish are dead in the lake? And what additional data or information do I need to figure this out, right? So talk with each other. I'm going to give you another piece of paper. Actually, you know what? I'm not going to give you a piece of paper. Turn it around. We're going to conserve trees. Turn it around and use that. Oh, no, I'll give you a piece of paper. All right, it goes through. So Fayez is going to come around with a piece of paper. So think about these things and see if you can take 5 to 10 minutes to draw a quick model of this system. So again, take a minute to get up and look at the other drawings of systems that people have, and feel free to talk to each other if you have questions about other people's systems. Because in 5 minutes you wrote down a lot of information already. So look around the room. So look around. Okay, so please return back to your seats. So as you notice, through this lens of systems, it helps you focus on what are the things that may be important, right? So, because if you look around the room, you all have a lake, but many of you included things around the lake. So how many of you have rivers, or talk about rivers that go into the lake, right? How many of you talk about the land around the lake, right? So the land around the lake, maybe there's people, and people usually do bad things, like, you know, they put fertilizer or, you know, chemicals on their lawns to make the lawn look nice, but that may kill the fish. How many of you have things that come out of the air that could affect, like acid rain? And that connects to factories down the line. So by doing this, just very quickly, it helps you to focus on what do I need to know, right? Are there people around? Are there factories around? Are there streams coming in? What's the quality of the water in those streams? And again, this morning, one of the speakers mentions the power of having students ask their own questions. Well, this can set students up to ask their own questions, right? So, what I would like you to do is that, why is it not? All right, I'll do this. Can you forward? Because I always think it's important when you attend a workshop to give you 2 minutes to think about what you learned here. How can you use this in your classroom, right? So write down one thing that you learned in this session that you could use when you go back in your classroom, or if you have a different role in your school. So write it down for yourself. Okay, so as I mentioned when we started this, they asked us to shorten the session because the initial session went over, so I had to skip a few parts. I want to point out, yesterday we did a whole day institute, some of you were there, and tomorrow afternoon I do another session on a different cross-cutting concept of matter and energy, focused on helping students to keep matter and energy separate, because often we confuse matter with energy, and it's a problem with students, and it's actually a problem with people, you know. So we have to keep it separate. So if you're interested in that session, it's at 14:30, so 2:30 in the afternoon. So thank you for being here, and enjoy the rest of your conference. Yes, we'll be here. Yes. So thank you and have a great day.